So welcome everyone to the GOCC. Today we have Gai Park talking to us about Naruse hook length formula and for mobile posets. But before we get started, just a quick reminder of our community statement. So last time we did a little longer introduction of it since it was the first time of the semester, but today it's just top 3 things we gotta remember. We're all learning together and everyone has something to contribute and no one has all the answers, not even the speaker. So if you have questions, put them in the chat and the speaker can read them from there, or one of the organizers will unmute ourselves to ask the question for you. Or you can unmute yourself if the speaker is okay with that and interrupt. And so with that said, thanks everyone for tuning in, and Gai, take it away.
All right, thank you so much for the introduction and lovely statements to keep in mind for the seminar. And I am happy to have any questions in the middle of the talk. Feel free to stop me, unmute yourself, and ask. So here is what the overview, what I plan to go through today. I will talk about some background information about the hook length formula and introduce you to a Naruse hook length formula and talk about their 2 analog. And then I'll also introduce you to this new set of posets called mobile posets and briefly talk about the method of the proof, and also, if we have time, talk about the case of the inversion index. Sorry, for some, I have a problem controlling my slides. There you go. All right. So first things first, we have a Young diagram, which is given a partition. We can represent it as a Young diagram. And here I have 2 examples of a partition of 7 into 3 to 2 and 2 to 1, drawn in Young diagram of English form, which I will be using consistently throughout this slide, this presentation. And given a Young diagram, we can look at the hook of an element, which is all the cells below and all the cells to the right and the cell itself. And combining all that, we have a hook length. So if I want to figure out the hook length of this blue box, then I would have to count all the column, which are the pink boxes, and all the cells to the right, which is the yellow box, and the cell itself. So the hook length of this cell would be 4, given this formula over here. Now, given a Young diagram, we can fill in with numbers and make it into a tableau. Here we have a standard Young tableau where we're filling in from number 1 through n, such that it is increasing in rows and columns. And here are 2 examples of the same shape of Young diagram, but different standard Young tableau. So you can see that there's no one unique way of filling this in. And so the question is, given a fixed shape, how many number of different standard Young tableau we can build? And in general, counting this number is interesting because it gives off combinatorial properties of other algebraic objects out there. One classic example is that it gives the dimension of irreducible representations of symmetric group Sn. So here we have a symmetric group S3, which has 3 irreducible representations corresponding with these 3 shapes. And there is one way to fill it out for this shape, one way to fill out for that second shape, 2 different ways to fill it out for this shape. So which corresponds to the fact that the dimension of standard representation is 2. So we can count this number using the classical hook length formula by Frame, Robinson, and Thrall. It's a beautiful formula written as a product of 1 over all the hook lengths. So here's an example. In blue, I have the hook length of each of the elements. This is not a standard Young tableau. As you can see, it's not increasing. But if you just take this cell and count all the cells below and to the right and the cell itself, you can see the hook length of this element would be 5. Plugging in all the blue numbers into the formula, given this fixed shape, you would have a total of 14 different standard Young tableau. So now let's talk about the Naruse hook length formula. We can generalize a Young diagram into skew shapes by taking a subset mu of lambda and coloring in the corner or shaving it off. So here I have examples of 3 different skew shape Young diagram with same lambda but different mu. And later on, I'll be working with specific type of skew shape, which is a border strip, which is a connected skew shape without any 2x2 squares. You can think of it as a single width ribbon. So for example, this is not a border strip because it has a 2x2 square here, it's too fat here. This is not a border strip because it's disconnected, and this is going to be a border strip. Okay. And can't go on. Oh, there you go. And again, we can fill this with numbers again, increasing in rows and column, and these are the examples. And you can already see that for skew shapes, we have more degree of freedom in this corner. This corner is not restricted by whatever is above, so it doesn't have to be 3 or bigger anymore. It can be small as 1 actually. So it has a little bit more complexity. And the question is, can we count the number of standard Young tableau for skew shape as well? And unfortunately, there's no known product. I should probably specify this. There's no known product hook length formula for the number of standard Young tableau for skew shape. Until Naruse came out with this new type of formula called Naruse hook length formula, which really resembles the hook length formula, except that it sums over this object script E here called excited diagrams, which I will explain in the next slide. So now that we have this, some combinatorial, the original proof by Naruse was given using highly algebraic things, but combinatorial proof was given by Morales, Pak, and Panova based on the case of, only for the case of the border strip. And I'll kind of explain why. And asymptotics of this number was also studied by Morales, Pak, and Cassidy. So let's talk about excited diagrams. These diagrams are obtained by sequence of this move called excited move. Basically, we start off, I'll be giving a recurrence definition for excited diagram for now. We start off with the skew shape where the lambda is white, uncolored, and the mu is colored in. And whenever we see this shape, this 2x2 pattern where there is a color here and everything else is white, we get to shift the colored box down. So let's do an example here. We see that pattern right here. And can you guys see my mouse moving around? Is that okay? Thank you. 2x2 shape right here. So we can move the box down diagonally, which opens up this box. It couldn't move before because it's not the same pattern. But now it opens up this box, and now we have that 2x2 pattern here, so we can move this box down diagonally, and this move will terminate because this color box can't go anywhere else. This tells us that there are a total of 3 excited diagrams for this particular skew shape. That's like one definition of excited diagram. Naruse gave like very specific technical definitions, which I attempted to read, but I haven't really fully read or understood. But I think this is a really good way of explaining what excited diagram is. Another way to think about, especially for the cases of border strip, is that the excited diagrams are actually the colored green boxes. But if you focus on the complement of the excited diagram, which is a white part, it actually is kind of like a lattice path from one corner to the other that kind of shift through as these color boxes move down. So that's another interpretation of excited diagram, and this combinatorial property allowed Morales, Pak, and Panova to come up with the combinatorial properties and explanations for the Naruse hook length formula.
I have a question. So you said the excited diagrams is now just the colored boxes. I thought first it's the white diagrams, but then the part. So the white part does not need to be a skew shape. Is that correct?
The original white part would need to be a skew shape. So we start off like this. So then if it's not a skew shape, then like there wouldn't be this particular shape for
Exactly, yes.
color thing to move, and then there will just be truly one excited diagram, which is just a shape.
But in between it can be any shapes, the complement.
Yeah.
Okay. But in the case of border strips, it's always, again, a border strip, I guess.
Yeah, exactly.
Okay.
You can kind of generalize this for like a thicker shape. Unfortunately, no,
Okay.
I don't think I have a thicker shape example here, but in my other projects, I look at the decompositions of thicker shapes of skew shape diagrams. So if you do excited diagrams, you can see like decompositions as lattice pad, and they like start shifting around.
Oh, okay. Thank you for clarification.
Another question that may be coming up later or not. For some reason, I'm visualizing these lattice paths as some interval on Young's lattice. Does that hold up, or is there some detail that says like they're not quite intervals that give you these excited diagrams?
I don't think I have a direct immediate answers to that right now. Yeah, but I think I would kind of look into it.
Okay.
All right, great. So let's do this example. Oh yeah.
So starting from single diagram, you can have, so in this case, you just went in one direction. You did the first step and then you did the second step. So instead of that, you can have two choices for the first one, and then you can have like a branching.
Exactly.
Possible, right?
Yes. Yeah, if this is a thicker shape, then there will be a bunch of like actual, lattices of this posets of all these possible moves and things that you would have.
And is there a counting for, how many are possible?
Oh, yeah. I think the immediate answer for how many excited diagrams are there for general shape isn't out yet, because I know like immediate answers for special shapes of skew shape. If it's like a zigzag, then it would be like a Catalan number, or a generalized Catalan number. But I don't know about the general skew shape though.
Right. Okay. So like they're going downwards, so we can at least like have a termination. So because like the color box are going downwards.
Yeah.
So, okay. Fine. Okay, cool.
Yeah. Okay, great. I love all these questions, and now we are actually understanding what the excited diagrams are. Let's actually try to work on this example as well. Again, in blue, I have the hook length, and we are summing over the excited diagrams, right? So there are 3 excited diagrams. So each of the fraction corresponds to the excited diagram. So let's look at this one. We're looking at the complement of the excited diagram according to what the formula is saying. So 3, 3, 1, 1. And then this shape. So this is another like thing. I think one of the questions was like, what are these intermediate objects? We gotta again look at the complement of the excited diagrams of 4, 3, 3, 2, 1, and then complement again. Putting all this thing in, we have the whopping 9 that I promised in the previous slides of standard Young tableau of this particular skew shape. All right. Now let's take it up a notch into a Q analog case. So in general, we can generalize these tableaus into semi-standard Young tableau, where we are increasing again strictly in column and weekly increasing by rows. So we're now, for my example, I am allowing zeros. Now I can repeat numbers, and there are a bunch of semi-standard Young tableau, infinitely many of them of this particular shape. There you go. And these are also related to short function of Q analog. So take the entries of all these tableaus and let them be the indices in these x's, or change them into x sub I into q to the power of I. We have the Q analog of short function, and they can be defined as a sum over the semi-standard tableau. So I believe I have there you go. I have actually worked it out here. So for this particular shape, I have 2 zeros and 2 ones, summing all of them. I have q to the power of 2. Here I have 2 ones and 1 2, summing over them, I have q to the power of 4. So if I sum over all of these q's in the polynomials, then I would have the Shor function in q analog for this particular shape 2 2. And this is also true for skew shape as well. And of course, for straight shape, we have the Q analog of the hook length formula. It looks almost like the original one, except we have this little accessory here, B lambda, where we are basically just think of it as if you just have a reverse plane partition and you are adding I-1 to each of the rows to induce column strictness, and then that's how the proof of this formula works. But I think I'm just saying too much without actually giving any slides. But I can talk more about that if anyone has any questions. Analogous to that, there is a Q analog formula for Naruse formula as well. Looks very similar to the Naruse hook length formula that sums over excited diagrams, but there's another accessory here, WD, which is a sum of hook lengths of the supports of these objects called broken diagonals. More objects are coming up. I will define them in the next slide, but you can see that these are the Q analogs of the previous formulas that I've shown you before. Let's talk about broken diagonals. They're still related to excited diagrams. So same thing, whenever we see this 2x2 shape, we get to slide the box down. But we have these diagonal arrays that comes from the original straight shape. So we have a bunch of these subdiagonals that will get pushed by the mu shape like this. So these are the diagonal arrays of the skew shape. And then you can also kind of think of these as like a pathway for the excited diagrams to move. So for example, if I am to do one right here, then this box would move downward diagonally to here, and this blue diagonal will be broken off and the segment will be going to the left. And there will be a blue segment here, excited diagram here, and then the rest of the blue diagonal here. So these will all be broken, and there are unique broken diagonal structures that corresponds to the excited diagram. Unfortunately, again, I only have thin shapes because I'm working a lot with border strip for this thing. So I don't really see the brokenness of the broken diagonal, but these would be the broken diagonal of the border strip examples that I'm working with here. So we start off with the original arrays that gets pushed from the mu. And whenever we are moving this colored box down diagonally, we are shifting this segment to the left. So we have the broken diagonal that gets shifted to this side. Again, this moves down and this gets shifted to this side. Any questions about broken diagonals?
Yes.
Yeah.
So from an initial state where I have a legitimate skew diagram, diagonals coming out of corners, no, just the bottom right of boxes. Okay. But once one of these things floats out, then if diagonals can kind of enter into the bottom left of boxes and disappear, so they won't continue onward. Like by having a box float, I won't then have two parallel diagonals right next to each other. Okay, so I can think of it as like the bottom left corners of boxes absorb diagonals.
So it does actually, no. It does not absorb.
It doesn't? Okay.
Doesn't absorb, and I think it brings up a really good point, and I want to annotate, and I can't seem to bring up my Zoom control for some reason. Difficulties.
Let's see if I can give you that power. That's-
Oh, no, I have it right here.
I made you a co-host, so that might
Oh,
have
thank you.
fixed it.
Thank you. So here is the box that I'm gonna move down, and then there will be the excited diagram that's now here, right?
Yes.
And then there will be that blue segment will be shifted to the left like this.
Right.
And then what that happens is that gives a pathway to now this excited diagram that can also move down, and it will keep getting shifted to the left.
Right.
I'm
going to see if I can add to this annotation.
Yeah.
So my comment was when I'm going to do a little bit of erasing. Nope, can't erase that. Was when that moved down, my new diagram, what I'd want to have happen, draw like this, is once this box is here, then there wouldn't be a box here. So this thing would shoot out a line, but then I want to keep drawing this diagonal. And I'm saying I wouldn't keep drawing that diagonal because it hits a box.
Yeah, exactly.
Okay.
Yes. Yeah, so it won't be producing any more new diagonals, just the existing one shifting around to the left as the excited move happens.
I think I understand what's happening. Thank you.
Okay, perfect. Yes, I love talking about this. So please give me any questions. And there's all these sorts of and more I study about these. There's like new ways to characterize them and new ways to think about it. So this is great. And let me cancel my annotation so I can move on to the next slide. I believe it's an example. Great. So let's do the same example now in Q analog. So here are, again, blue are the hook lengths, and this is abusive notation where this bracket 3s are those binomials, 1 minus q to the power of I. And now in the numerator, I have to sum up the hook lengths of each of the broken diagonals. So there are 3 broken diagonals here, and the hook lengths are 2, 1, 1. So I must sum them up here in the numerator. Same thing for this one, 2, 3, 1. Same thing for this one, 1, 3, 4. And I would have this infinite polynomial that would be the short function of this particular skew shape. And let's actually kind of work it out. For this particular shape, the smallest possible semi-standard Young tableau coming from here, it will be 0, 1, 2 and 0, 1. So if you sum all the entries up, it will be q to the power of 4. So it makes sense that this polynomial starts with q to the power of 4. Okay. So let me introduce you now to mobile posets. Let's talk about now posets and linear extensions. Given a poset, a linear extension of P is a linear ordering of the elements such that it is compatible with the ordering of the poset itself. So here we have an example, A, B, C, D. And given this poset, B and C are unrelated to each other. So the linear extension is an ordering of A, B, C, D such that A always have to come before B and C, and all of those have to come before D, and the ordering of B and C does not matter, which gives us 2 linear extensions. And E of P counts the actual size of the set, so we have E of P is equal to 2. Right? And in general, counting the number of linear extension is really hard. And I think the correct term is sharp P, proven by Brightwell and Winkler, if anyone is into complexity theory. All right, so why am I suddenly talking about posets and linear extensions while I was talking about tableaus before? Well, given this poset that I have, if I like rotate it 90 degrees to the right for this example, then I would actually have a tableau like this. And then let's look at the linear extensions A, B, C, D, and to wherever the positions of each A, B, C, D is, we would insert that number into the boxes. So A is in position 1, so we put 1 here, B is in position 2, 3, C is in position 3, and D is position 4, and we have a standard Young tableau. B and C can be switched So 2 and 3 can be switched. And the fact that if I'm trying to make a standard Young tableau out of this shape, it doesn't really matter what it is, as long as B and C is bigger than A and smaller than D. It's an equivalent statement to the fact that for linear extensions of this poset, B and C must come after A and must come before D. And this is true for general case as well, even for skew shape in general. Given a number of linear extensions of a poset derived from that shape of the Young tableau, Young diagram, is equal to the number of standard Young tableau of that particular shape as well. True for both straight and skew shape. So given any tableau like this, we can like rotate it and pretend that, well, I guess it's this rotation for this one, rotate it and view it as a poset, where the I think convention may be different for some people. For me, for this example, at least, it seems like this corner A and C are the maximum elements and the E and B are the minimum elements, but it can also be flipped. And there are, of course, two analogs of linear extensions as well. For two analog version, we will be working with labeled posets. So we will now label the posets with 1, 2, 3, 4, the numbers, and we'll be looking at the words, the ordering of the linear extensions according to that label, and look at either some statistics of them. And then the two popular ones are the major index and the number of inversion index. Given as this definition, where the major index looks at the position of the descent and sum them all over, and the number of inversion is the number of times where the follow-up label is less than the one that's previous. I'll give out an example. Okay, let's do major and inversion for this particular example. So first, we need to label this poset. And I am going to label this 1, 2, 3, 4 like this. And this is a short labeling where I am increasing in this direction. So I'm increasing in this direction, going by this row, this row, this row, and this row. Okay, so ABCD now corresponds to 2, 1, 4, 3, and a CBD now corresponds to 2, 4, 1, 3. Let's look at the major index. The descents happen from 2 to 1 in position 1, 4 to 3 in position 3. Adding them up, we have 4. For this one, descents happen in position 2, and that's it. So we have this finite polynomial q to the power of 2 plus q to the power of 4 as EQ major index. For inversion, let's look at this, if I can do this right. 2 to 1, there's inversion 1, and 4 to 3, that's inversion 2, so there's 2 of them. For 2, 4, 1, 3, we have 2 to 1. For inversion, it doesn't really matter how far you are down. There's inversion 1, 4 to 1, 4 to 3, that's 2 inversions, and that's it. So we have a total of 3 inversions for that linear extension. So this is our polynomial for EQ of inversion. Any questions so far?
So this very much depends on your labeling, right?
Yes.
Like if you, okay.
Yes, it very much depends on the labeling. And I'll talk a little bit more about labeling in the coming slides.
Okay.
Right. So given this particular short labeling, EQ of the major index is actually correspondent to the Shor function, or the semi-standardness of that tableau. And I believe if this labeling is a natural labeling, then it corresponds more to the RPP of that tableau. So different labelings would correspond to different types of tableaus. I only know natural and Shor labeling for now, but it's kind of interesting how it works like that. And then, so all of these Shor polynomials that I've shown you before can actually be related to, you can write it again like EQ of the major index of the posets divided off by the certain things. Keep in mind that this was an infinite series while this was finite, so we just have to kind of divide it off to make sure that they are equivalent to each other. I think that's it for this slide. So let's do an example here again. So everything in EQ major, we already did all the Naruse formula in the previous slides. So let's just convert this into EQ major slides and then EQ major stats and then see how that works. If I multiply this product, I would have this finite polynomial that corresponds to the major index. So if you are to write, and this is short labeled, increasing in this direction, going up row by row like this, if you can come up with a linear extensions, 5, 3, 2, 1, 4, and then look at the major indices of them, hopefully it would correspond to one of this. When I'm working on a board, I would write it on the board and hopefully one of them would match, and it has so far. I don't think I'm gonna try to do the annotation unless it's necessary for the rest of the presentation because I'm a little scared. Any questions or comments about this example or major and inversion index?
So this may have been me losing focus. I noticed that when I evaluate Q is equal to 1, I get 9. And I believe that was the number of labelings. Am I going over something that's already gone over, or am I spoiling something?
Yeah, no. Going over something we've already gone over quite subtly, actually. So 9 is the number of linear extensions of this poset, which is also the number of standard Young tableau of this particular Young diagram. So yes. All right. So here's the question. We have this Young diagram, which has a very nice product formula, because Young diagram is equivalent to posets coming from Young diagrams are basically equivalent to counting the number of standard Young tableau of the Young diagram, which is given off as a hook length formula. And we have border strips, which is given by a Naruse formula. Is there any way to combine them together to make a more generalized poset, and that we can have a better formula to count those generalized posets? And in fact, that Young diagrams that behaves very nicely by having this product formula can actually be generalized even further into the complete posets. So we can combine basically, so we can see them as the same thing. I'll talk a little bit more about the complete in the next slide, but we can combine the complete posets and border strips together, and now we have this super poset called mobile posets. It was originally introduced by these 4 people, and we are basically taking a border strip or some kind of skew shape that hopefully we'll be able to generalize in the future. But for now, we'll be just working with border strip, and we'll be hanging the complete posets all over, and we have a mathematical mobile here. Fun fact, for some reason, when I was working on this for a couple of months, it didn't hit me this mobile is those like baby toy mobile. I always thought like mobile is like phone company or something. So I had no idea how the name would correspond to the shape. But when I was making this slide long ago, I like Googled mobile and this popped up, and it finally made all sense to me. So I just wanted to put this picture here too, so that you guys have the realization sooner. So what are the D-complete posets and why those? So these posets are a large class of posets, including the Young diagrams that I talked about, but it's not limited to just that. It includes also rooted trees and shifted Young diagrams, and they behave really, really nicely. Sorry, I also just realized that there's a chat. Thank you. So they behave really nicely, and what I mean by that is that they all have this nice product formula. Peterson and Proctor have shown that these complete posets all actually have this very nice product formula. So we can count the number of linear extensions of these very nicely. We can also count the major index and the inversion indices of this for any labeling, very strong statement. The complete poset of major index is given by this formula. And unfortunately for inversion index, for some reason it behaves in a very annoying way, and we don't have the formula for general D-complete posets, but we only have it for rooted trees with a very particular labeling. And that would be this formula. Okay, so when they first introduced the mobile posets, they were looking at the determinant formula to count the number of linear extensions of this. And now the next natural question is that because the main foundation is the skew shape, is it possible to have a Naruse formula to count the number of linear extensions? And yes, indeed, it turns out that it is possible to have a Naruse formula. We just need to define hook. We just need to redefine the definition of hook for this particular posets. So the hook now is take the original hook of the element and whatever extensions, the arm extensions of the D-complete posets that you have, you will add those sizes to your hook length. So here we have this hook. This D-complete poset is outside of that arm region, so we don't have to count that. This one is, so we would be counting the size of this D-complete poset, which is 4. So the new hook length of this element would be now 7. We also have the major index of the Naruse formula as well, where of course we are looking at the broken diagonals as well. And here as well, we are looking at the new hook length definitions of the broken diagonals. And I just put this formula here just so you can compare it and see the resemblance between the two. All right, so let's do this scary example here. It's the same shape where I just added 2 extra D-complete posets here. Again, in blue, I have written down the new hook length of only the border strip. The hook length of the D-complete posets is whatever you think it is. So it would be 1, 2, 2, and 3 for this particular shape. In red, I have put down the labeling that I am using. So I am just labeling the D-complete posets first, and then I am sure labeling the rest. I haven't played around too much with this, but because the original formula for D-complete posets for EQ major index was for all labeling, I believe this 1, 2, 3, 4, 5, 6, 7, 8 can be like switched around and it might still work. But I have to be honest, I haven't played around too much with the labelings quite yet. Okay, so we have all the hook lengths here. Sorry, I meant to highlight the bottom one. And 2 to the 12, those are the broken diagonals, right? So this element 5, this element 1, and this element 6 is the broken diagonal of that first excited diagram. So if I add them together, I have 2 to the power of 12. First one moved down, I believe this is now the broken diagonal. So it's going to be 5 plus 7 plus 6. Luckily, thankfully, it equals to 18. So I'm adding the right ones and then so on. So that would be the finite polynomial that counts in the number of linear extensions and its major index of this particular poset. And for the case when Q is equal to 1, this would be the case, and there are 33 thousandths of standard, no, sorry, not standard Young Tableau. I can't really relate it to standard Young Tableau anymore because these are mobile, but that many linear extensions of this particular poset. All right, so if I have time, I will just briefly mention the method of proof. The proof heavily follows the original proof given by Morales, Pack, and Panova when they were combinatorially proving the Naruse hook length formula for border strip. It heavily relies on its recursion formula. So basically, given the skew shape, there are these inner corners that can be seen as a maximal element of these posets. So how we can build these linear extension is take out one of the maximal element, which is U for here, and then we would have two disconnected posets, figure out the linear extensions, and then just attach this maximal element at the end, And that's how we are building off all these linear extensions. So we have a recurrence happening. And turns out that if the recurrence happens really nicely, that we just need to shift it by the size of one of the disconnected posets. So we have this new lemma to look at the recurrence of these linear extensions, and we were able to prove it. For counting the number of linear extensions for two disjoint posets, Stanley has a very nice propositions to count using this formula. There is a problem though with our case in the major index. So let's look at this. I am removing 12, the maximum element, and trying to build my linear extensions. So we have linear extension combinations of these two disjoint, and I'm attaching 12 at the end. If the penultimate element in the linear extension ends with 9, and if I add 12 at the end, there's no extra major index happening, and that's fine. But if the penultimate element ends with 13, and I'm adding 12 at the end, we have an extra major index for that particular sets of linear extensions that ends with 13. So now we have to figure out, okay, of all the linear extension combinations of the disjoint posets between these two, we have to distinguish which one ends with 9 and which one ends with 13, so we can shift the appropriate one when we add 12 at the end. So we had to dig in a little bit into p-partition and then figure out how that would work. So I briefly mentioned p-partitions here. So let L of this, the linear extension, set of the linear extensions of this labeled posets, semicolon S, to be the linear extensions that ends with that particular element S. And we will define the number, the EQ of the major index of semicolon S to be the functions for that particular linear extension. Then we can count the number of linear extensions just with the ones that ends with that particular element S, so that using this formula, and then we will shifting just those, and then we can leave the rest as is. So this was one of the necessary steps to figure out the EQ of the major index for my posets. So let's just to do some final conclusion and visualization here. Here, I am trying to distinguish which ones are the one that just ends with 13. So because my labeling of this would be 13, and then I will be plugging in rest of the formulas here, and these would have the extra major index at position 12, and the complement of these will just not have a extra major index. So now I can actually distinguish these out. All right, let me briefly talk about the case of inversion index. All my talk heavily depended on major index, and those turns out to be usually the more interesting one anyways. So I do have it here. Here is the formula for the inversion. Couple of things to note. One of them is the fact that this is not just a general mobile poset, it's a tree mobile posets, because recall that for the inversion index, we didn't have a formula for all the complete poset. We only had it for the trees. So that would tell us that my mobile poset also has to be trees, because I can't attach any incomplete posets anymore. Another thing is that there are all these like annoying accessories that kind of I have to attach here and there to make it actually work. Look at my major index formula. It looks really nice and clean, and it resembles with the original Naruse Skew analog formula very well. Whereas my inversion formula, there's all these like other ugly stuff there that I'm not really happy about. And so this slide is the points that I just talked about in the previous slide, the restrictions on the case of the inversion index. And of course, one of them I just talked there is not for generally complete posets, it's just for trees. And the other one is that it has a very restrictive labeling rules. On the slides where I was talking about the proof, I mentioned the proposition given by Stanley to count the number of linear extensions of two disjoint posets. There's one for inversion index as well, but then again, inversion index are very annoying and they need a very particular condition. And one of the condition is this labeling condition where label of every element in P has to be smaller than the label of every element in Q. So this condition has to also work for me to use this property to prove my formula. So I have to make sure that my mobile posets are labeled in this particular way. So I have figured out a way to label it like that. Given a mobile posets, tree poset, I will segment it by its maximal element. And then I just have to make sure to, again, label the trees naturally, because that was another restriction, and then label the rest using my short function. So, short labeling. We have this to be labeled first. That must be bigger than this labeling. That has to be bigger than this labeling. The other way around. P4 has to be bigger than P3, has to be bigger than P2, and then P1. So then, I cover 2, 3, and 4, and just look at P1. I would label the hanging trees naturally, and I would just label the rest 4, 5, 6. Now I have to start this guy. I have to label the hanging trees 7, 8, 9 naturally, and then label the rest as I would, and then so on. So this assures that every labeling in Pi+1 is bigger than all the labelings in Pi. So just annoying stuff that I wasn't too happy about when I was working with inversion index. And here's an example. In red, I believe it is the labeling of this posets. I inserted into my formula, and this would be the final answer that I will be getting. You can check in Sage if you would like to. All right, that is it. So far today, I talked about a lot about hook length formulas and introduced the Naruse hook length formula, and talked about the mobile posets and the Naruse hook length formula for those mobile posets as well. Thank you. That's all I have to say for today. Yeah.
All right, let's thank Gai for the wonderful talk. And any questions?
And thank you for people in the chat. I'm glad people enjoyed it. I really enjoyed interacting with a lot of questions throughout the talk as well.
You made it very easy to follow along.
Yeah,
very enjoyable.
I hope that's okay for the video. But
it's great.
Okay, all right. Some glitch here and there, but all worked out fine.
I do have one question. So if I think of a Q analog, I always want to plug in roots of unity for Q because of cyclic sieving phenomena. And if I remember correctly, if you take the regular Q analog for the hook length formula, if you plug in integers, roots of unity, you will get some integers which count the number of border strip tableau. And my question is, do you know if some similar stuff occurring in your Q analogs?
No, I don't think so. And somebody did ask about possible cyclic sievings for these mobile posets as well, and I have not looked into it, but that's actually a kind of interesting thing that I might want to try. Yeah, sorry I can't answer, but that's a really interesting point.
Thank you.
I ended up with lots and lots of questions, so I want to encourage people to head me off before I get ahead of steam. But so the first overall question is the hook length formula for your mobiles. That was that's just counting the number of elements of a poset that are less than the elements of your poset. Like once you put it on its side.
Right.
Okay.
Well, yeah, it will be counting really the linear extension of that poset, really.
Well, sorry, not the hook length formula. Sorry,
Yeah.
the hook lengths.
Oh,
Like the box has a hook length of 7, and I think the way it was counted, it was just the number of elements less than that element in your box.
Yeah, the hooked length definition of the complete poset is also one of those definitions that got too technical, and I attempted to read and I just never got to it. But so here is a the complete poset, right? I will be looking at this like a Young diagram, like this.
Mhm.
So hook length of B would be
So
would be
okay,
1,
yeah, the
2,
hook length
and
here, yeah, would be 1. But when you get to your mobiles, you
and I have an example.
yeah.
So the hook length of the
So the elements in the mobile. So you've got your 7 element that's labeled 7 right now.
yes.
I believe there are exactly 7 elements to the post set less than or equal to that element.
Yes, this one, and this one. Yes.
Okay.
Yeah. Because the definition of my definition of hook for this element would just be whatever your hook length is, and then I would have to add the size of the complete poset. So it would be that.
Okay. Yeah, I've got lots of other minor questions, but I want to pause because I've got like 6 things written down here.
Yeah, it was kind of dangerous for me to think hook length as like all the elements below, just like simply as that, because depending on what kind of post that you're working with, like definition of hook kind of is different. Like for example,
Right.
like here, yeah. So like, yeah, in this case, it would be exactly that because of the size of the decomposed post.
Mhm.
Yeah, so in this case, you have tilted the Young diagram not by a lot. Like, so is that why we're using the reverse shoe labeling?
Sorry, what was the question?
Okay, so in the previous just the square diagram, you had that go like a complete 180 kind of thing.
Yeah.
So in this case, it's lesser. So is that why it's reverse?
Yeah. So here was a
like
story.
topples over.
When I believe in Stanley's book, when he is translating between Tableau and Poset, he rotates it in a certain way and then labels it. For some reason, when I received this project and I was rotating Posets and Tableaus, I rotated the opposite way. And by the time that I realized it, it was too far into my game to change it all back. So I believe it's all the same thing. It's just that, I had to reverse the labeling, but I am like 90% sure that it is the same, different convention, same story. Yeah, I always like wonder if I should just take away the word reverse to just save myself explanations, but yeah.
All right. Any other questions?
I think I have got one more that I can fit in the recorded time.
All
So
right.
whenever you're creating those you're trying to do an inductive process where you're taking a maximal element, removing it, and then breaking the post set into 2. What happens if you've hung a D post set from the maximal element?
Right here, right?
Yes.
Yeah. And I am counting those examples as well. They would be part of all the, they are now part of the disjoint sets now.
So it would be 3 disjoint.
Yeah.
Okay.
Yeah. And then like the math doesn't get any complicated. Actually, it works out, and I've done a bunch of those examples as well. It works out beautifully because they're all disjoint. You just combine all of them together, and those one would be less than 12 for sure, like all the labelings and stuff. So then all works out really well.
Yeah.
Yeah, and like we might be out of time, but like I'm happy to talk about this if you have any further questions, Mark.
All right, so let's thank Gayi one more time. Thank you.
Thank you.